We can have it out there for all those non-Zoomville people. Hopefully you're watching it at some point in the near future. All right, so real quickly, what have we done recently and what's due? Let me see what I can find. Okay, we have this construction project that we just finally wrote out last week because I was like, I'm never going to get this typed up. So the rubric is in your, what is that, week 10 from last week, I believe. And you're doing all those things by hand and then doing all those things in GeoGebra, and then you're writing up a comparison between the two. It's due on Thursday. So you've got a little bit of time to finish that out if you haven't done it yet, right? Yeah, I think some of you have already done it / gotten it off your plate, which is great. Come on, Jay. There we go. Okay, what else do I have that's not already done? We have this stuff about the semester long project that's due in November 17th, which is 2 weeks from today. Guys, Thanksgiving is in 3 weeks. So it's moving very quickly now as we slide on into the final exams. So your write-ups are due on the 17th. Your presentations are due on the 20th. We went over this in depth last week. So if you're not sure about it, go watch last week's videos again. As a point of clarification, because I did get an email over the weekend, the write-up is going to be submitted online in D2L, just like everything else we've done. I know in the original handout, it said that you're going to turn that into me, like hard copy, but we've changed our formatting for our class this semester, so we're not doing that. So it'll go in D2L just like everything else. And you do not have to make copies of your presentation like you originally were supposed to, right? Handouts and activities and stuff for the in-class people, because again, they're not going to be here face to face. So if you have an activity that you want to share with the group as part of your presentation, then you'll either upload it into your discussions post. I think you should be able to do that. But if you can't get it to upload, you can just send it to me and I'll upload it in the document section for the week so that people can see it. So if you have something you want to share document-wise, we can still do that. Your videos are going to be in the discussion board. Exam 2, November 24th. That's the last day you're going to see me face-to-face unless you just want to come by my office or something like that. Okay, that's Tuesday before Thanksgiving. The 26th is Thanksgiving. And then I'll have your graded test back to you December 1st, along with a quiz for final exam options, and then review week and final if you're taking it, because it's optional, as we talked about. Okay? Not a lot left over for the semester whenever we start running into things like that. There are 2 major assignments, or I don't want to say major, 2 projects, let's say, that we're going to talk about right now so that you have them and you'll be done with them. And I think this is probably just about all the stuff I can possibly give you for the semester. So we're about done with getting assignments. So that's cool. So 2 things you need. One is the proofs, second set. Yay, the second set of proofs. Why is that so light? The second set of proofs, this one's on triangles and quadrilaterals. Okay, and all I'm doing here is just assigning a couple of sets of homework out of the book, but it will have the weight of a proof project, just like the first proof projects that we did on the special angles and stuff. So let me find that real fast. I'm sorry. It's either in the old book, and I decided what I'm going to do is I'm going to cut and paste and make it into a document and then put it online as well. But these are straight out of your book. So I'll post them because we have the two different versions of the book going. But if you want to look in your old book, the triangles are section 13.3, page 712, 3, 4, 6, 7, 10, and 11. And the quadrilaterals are 13.4, which is page 717, 1, 3, 4, 7, 8, 9, and 10. Okay, that's the one book. And then the new book, and you'll just have to figure out which book you have or wait until I can scan it and upload it into a document for you guys. Same stuff, the triangles are still 1 or 13.3, but it's page 688, and the quadrilateral still 13.4, but it's page 693. Okay, so this is a proof project, and I want to have it due before your exam. So let's make this due November 19th. That's a Thursday. The day we're going to do the review for your exam number 2. So that gives you, today's the 3rd, a little bit over 2 weeks to work on these. But like I said with the last set of proofs, do not put this off to the very, very last minute and then go, oh, I need to do, what is this? 13 proofs. I need to do 13 proofs in one day. That's probably not going to happen. Again, if you look at it, today's the 3rd. It's not due till the 19th. If you do about 1 proof a day, you're pretty good. But if you put it off until the 17th and you have to do 13 proofs, you're probably in trouble. Okay, so and here's a nice little thing. I actually have, so I want you to work on these and see what you can do. And we're going to work on them in class a little bit this week, so you're not totally thrown to the wolves. But I also have some hints that are already loaded in D2L. So like if you're looking at one of them and you're like, oh, I don't even know where to start. That's usually the problem with proofs, right? People just don't even know where to start. Then you can look at the hints that are already loaded into D2L. And I think it says something like hints for second proof project or something like that. And that's a document that's up in there, and you can say, oh, she wants me to use the definition of an isosceles triangle to do such and such. So you can use that, and hopefully it kind of points you in the right direction. That's my hope. Okay. So wrapping up the semester, there's that. There's a homework today. We might as well get it out there. It's the handout for 7.1. I think this is the last homework that I plan to give you. So that's cool. There might be one more, but I don't think so. It is in D2L already. I handed it out here in Commerce. We'll talk about it if you want to talk about it. It'll be due in 1 week. So we're going to talk about it as we go through, what is that? The 10th. No, 11, 10. There you go. Okay, there's a reflection still out there. Like I said, there's a quiz about the final exam. There's probably one more quiz going out for just participation. And that's about it. We're really kind of wrapping it up and finishing things up. So yay. There you go. All right, moving on. Questions, comments, nobody's yelling. Everything makes sense. Okay. If you have questions, just email me. We'll work it out. All right. In that case, then last week we had looked at the beginnings of transformations. And I mentioned that one of the things we do with transformations is tessellations. So I want to talk for a minute about what those are. I'm not going to go too deeply into them because, of course, we have people who are doing these for their projects. second. I need to steal some manipulatives. So a couple of different people are doing tessellations for their project, so I don't want to steal any thunder. We just barely started. We talked about transformations. Translations mean slide the object around. Rotations mean return the object around. And reflections mean flip the object, right? So we talked about those. And your book has a huge section on tessellations. All right, so the first thing people say is, what the heck is a tessellation? So for instance, one of the things that you might be asked to tessellate would be some kind of a two-dimensional object. So this guy is, what shape is that? It has 6 sides. Hexagon, yeah, we haven't really talked about them yet because we've kind of stopped at quadrilaterals. But we know that after quadrilaterals comes pentagons, those are 5-sided objects. And then after that comes hexagons, right? Okay, so the tessellation goes like this. You can rotate, reflect, translate, whatever, your object to tile the plane. That's the word that we want to use, is tiling the plane. And by tile the plane, what they mean is that they want it to cover the plane, but they don't want any gaps and they don't want any overlaps, okay? So if this particular hexagon will tile this plane, then I should be able to basically line up the edges of the hexagon as I go along and copy it over and over again. Now I'm just translating, sliding my hexagon around, right? To the side and up, to the side and down. But with this particular one, this is a regular hexagon, okay? Regular means that all the sides and all the angles, interior angles, are the same measure. So it's a regular one, so it wouldn't have mattered if I rotated it or reflected it or whatever. But in this case, all I need to do is translate, slide it over, and here we go. Okay. What I don't want to have to do is I don't want to have to, in order to cover things, I don't want to have one of my hexagons overlapping the other one. So I don't want them to share space. Okay. And what I don't want to do is I don't want to have to leave a gap in between my hexagons. So we're just making sure tiling means that I can cover the entire space without overlaps and without any gaps. What do y'all think about this hexagon? Think it's tiling the space? Yeah, so this will tile. Okay, so that means that this one will create a tessellation, okay? And this one's kind of a common one because it looks like that honeycomb stuff, right? So, in fact, a lot of times they'll call this the honeycomb tessellation, okay? So this is a great tessellation. Okay. Then the question comes up, well, which polygons will tile and which polygons won't tile? And I'm not going to answer that question because hopefully somebody who does one of my presentations on tessellations will have that answer for us. But I do want to think for just a minute about a couple of them. So what do y'all think about triangles? Summer says yes. Okay, does it matter what kind of triangle? Like here, I have a lovely equilateral triangle, and these are just my pattern blocks, right, from like a 1350 or 1351 class. Okay. Now, clearly I reflected or rotated or whatever you want to think, but what do we that looks like it's working, right? It looks like I'm not going to have to leave any crazy gaps or anything like that in my thing. And Summer said yes. In fact, if you remember pattern blocks from your 1350 or 1351 class, if I keep going with this, I've got 3 of them right now, but if I keep going and I make the second half down here, I'll actually end up with a hexagon, right? Okay, so if the hexagon would do it, then this nice, pretty equilateral triangle would do it also. Okay. But my question wasn't about equilateral triangles, it was about triangles. So what if I gave you some crazy scalene triangle? Hmm?
I think so, because you can turn him into a square, or no, a rectangle, and then he's copy and pasting the rectangle.
But we don't know anything about rectangles. Maria says all triangles will tessellate. Okay, but I like the idea that I've got over here from Ashley. She's basically saying I could make this into a quadrilateral. She said rectangle, but this one's not quite a rectangle, right? Doesn't have exactly 90-degree angles, but a quadrilateral. And then what? She thinks that I can just keep on repeating that quadrilateral is what she said. So like I could do something a bit like this. And I might have to, I don't know, offset them a little bit. Might not have to offset them, but depending on what I've got, I might not quite be able to make a really almost rectangle. I might make kites instead. So like I could have easily, well, here, I could have done like that, right? And made more of a kite. Not that one. It would have had to be like that. But anyway, you get the point. I could have made like a kite. And then I might have to rotate that kite or something like that to make it tessellate, but it sounds like it will. We think it will. So I'm hearing all triangles. So somebody will have to hopefully give us the mathy reason. By the way, this is a really cool art project type thing, and I like it whenever you can get kids to do math and more of a hands-on art thing, because a lot of times they have the really good art skills and it ties in their brain, basically left brain, right brain kind of thing. But this is not just an art project, okay? There is a ton of math that goes on inside of this. So hopefully on our presentation, somebody will have that. So Ashley says, if we can change the triangles to quadrilaterals, she thinks those will tile also. That's what I heard. Okay, so we'll see about that. What about pentagons? We know that the regular hexagon works. We don't know about irregular hexagons. Like what if this guy was squished down and oblong or something like that? Like my hexagon could be more like that, right? But a pentagon, that guy's weird. And it doesn't have to be a regular pentagon. Kind of a housey thing there. Okay. What about that guy? I don't know. So these are the things I'm hoping to hear from our tessellation group, because there are specific rules. And if they don't look, then we can talk about it like during the review for the final or something. Specific rules for which polygons will or won't tile the plane. And by plane here, we just mean the flat surface, right? That is our piece of paper in this case. So we'll have to think about that. There are rules about the angles, and that's all I'm going to say right now. Anyway, your book goes really into depth on tessellations, and I'm just not going to do it. So if you look, this is chapter 7. They talk all about So you can find some of your answers in your book. Tessellations with regular polygons. So let me throw some of this up here. So, and of course, they're much better pictures than what I could ever draw for you. So we're going to use their stuff and not my stuff, which is awesome. Okay, this is a bit of the honeycomb that we just did, right? Okay, but a much nicer picture. And this guy right here actually has a hexagon in it, but you notice it also has the triangles in it. Let me get closer. Let me try a little closer. Sorry. Okay, you see it also has these black triangles around it that are making it almost look like a star that it's tessellating. And clearly it's covering the plane there, right? So they're going to do different combinations of polygons. So what if I add this guy with that guy? What if I do this and this? So when they say regular polygons, they're not just talking about a single polygon like the hexagon. They're talking about combinations as well. So here's another picture, a couple of pictures. Look at this guy. This guy is what? An octagon with basically a quadrilateral, a diamond. Okay, so maybe the octagon, just look at those octagons. Would the octagon tile this area by itself? No, because it would have these gaps in here, right? But maybe the octagon with the square or quadrilateral in it does do the entire area. And then they get kind of complicated. These are circles, right? So circles with the little triangles in between them. They're not quite circles, are they? Dodecagons. What's a dodecagon? Okay, think deca. What is that in the metric? Deca? 10. And do means 2. So dodecagon is 2 plus 10, 12 sides. Dodecagons. And you can see this almost, I thought they were circles at first, right? They almost look like circles because they start approximating a circle. But look, they got this with a hexagon with a square. Okay, and if you add in the right pieces, you can see, yeah, it's tiling. Interesting. All right, over here they have a combination of squares and triangles. So they've done some interesting stuff in here. Like I said, I'm never going to be able to draw those. They have cool patterns. This nice star pattern. This reminds me of quilts, which is one of our topics for our semester-long project. So if you've got quilts, you can look maybe in chapter 7 for some help. So some other sides. Oh, Maria says 12 sides. It is. Thank you. I'm sorry. I didn't read fast enough. All right. So they have questions about, do all triangles tessellate? They have investigations for that. All quadrilaterals. Investigations for that. So it sounds like you guys might be onto something there. I'm trying to get to some of their other tessellations. Tessellations that use only translations. So here's some examples. So all they did was slide it around. Okay, they've got this cool Pegasus thing and the red Pegasus. So you can see they slid it around, but you're getting the inverse picture basically. That's cool. And then they start talking about Escher stuff. I actually have a video, and I'm looking at one day toward the end of the semester. I'm going on a trip, and I might accidentally give y'all a video day instead of meeting face-to-face. And so I already have one where you can create your own thing that's a weird Escher type tessellation. So I might give y'all some of those videos to watch. This is a famous Escher drawing, the lizards. In fact, it's right outside. I think it's still outside our door in our classroom. And you can tell that the lizards kind of interlock. Their tails go in between the legs of the other lizard. And this one's done with rotations, right? They just take that lizard and keep on spinning him, so to speak, to fill in the gaps. I'll tell you a week before, once I make a final decision. Sorry, Maria. I'm not sure about that date yet, so I don't want to make it final. Okay, here's an Escher type one where they're rotating. Really cool stuff. Here's one where they rotate and slide. I'm sorry, reflect and slide. So So we call them glide reflections. The whole chapter is all about tessellation. So if you're doing yours and you're still working on it, and you're doing tessellations, then there you go. Okay. That's about all I'm going to say about tessellations. Oh, come on. You're welcome. Okay, here we go. All right, so that's kind of my rundown on tessellations, and I'm not going to do a ton more with that because, again, somebody else is going to do it for me, I hope, very succinctly. I have a couple of cool pictures here that I brought with me. I'm going to show you real fast. Then we're going to do the very last thing for translations and stuff, transformations, and then we're going to move on. Here's an Escher one. It's not quite what we would think about. And so he's known for some more abstract art, so to speak. So you can tell they start out as geese up here, right? And what he's doing is he's using what he considers the negative space. Okay, so if the goose is the positive side of things, it's a black drawing, then the white would be the negative spot, the negative space here. So as you follow it down, you can still tell it's still a goose, right, as it follows down. But as we get through here, we're like, oh, it looks less and less like a goose and more like just kind of a blob in between, right? And he's kind of expanding a bit because you can tell this, or actually contracting in this case. Here the goose is pretty big, but when I get down here, you can tell this space has been squished some, okay? And so it doesn't even have the same shape. And then when you look at the negative space, it was just like air between the two geese, right? But as I get down closer, you can tell he starts filling it in and making it look more and more and more like a catfish. So now when I get down to the bottom here, or whatever kind of fish that is, whenever I get down to the bottom, the fish is the actual positive space. And now the negative space is the black space that's around it. Okay, so the space that's not in the picture that I'm looking at. So it's a really weird, mind-blowy kind of thing. I'm not sure what all drugs he was taking at the time. No, I'm kidding. So it's interesting because Escher sketched these by hand. So, and he managed to use some weird stuff in it. What?
Jeez.
Yeah, I know, right? It's pretty detailed for like hand sketching. So yeah, and there are like original artist renditions of stuff that would be actually really, really expensive. We have some of the prints of some of his stuff in the math lab and around the department and different things. He's just got a cool perspective on stuff, so it's a little bit different. Here's the lizard one that I just showed you a second ago that I said they use rotations for these lizards. But it's more of a, okay, what if these lizards were coming up off the page? You can see they're coming to life here. They go up on the book, and come back over here. And they go back down through this goblet or whatever, and then they're going back onto the page. So again, I'm not sure exactly what he was taking, but it's an interesting perspective on what normally would be a very mathy tessellation project. Okay, and one more. And I loaded all three of these pictures into your D2L so you can see them and play with them more distinctly if you want. This is another one where he's kind of done a compilation of things. He's got what he considers a devil, and here in the black, and an angel here in the white. Devils and angels. And that's the name of this particular picture. And you can see how he's using, again, that negative space in between, for instance, his devils to fill in with his angels. And one angel's facing this way and one angel's facing that way. So kind of some interesting and different stuff. This one, I believe, would almost qualify, or probably does qualify, as a fractal. Because as I get out here, it's these duplications over and over that we would do it for infinity. So, kind of a neat thing. Heaven and Hell is the official title. Sorry. So, there you go. Interesting, weird stuff. that people do with these things. Yes, they do. I know. I'm not nearly that creative, so that would not help me a bit. All right, let's talk about the homework I just assigned. It's the 7.1 transformations and symmetry. The only thing we haven't really talked about is symmetry, so I'd like to throw that out there and make sure we have kind of a definition and we can identify different kinds of symmetry. And then I think that you'll be able to do these translations and stuff. They use the grid here to do some translation. So if it says, you know, translate means slide by this given vector, that means they want you to follow it that direction. Okay. So let's talk about symmetry. What is symmetry? You all had to work with symmetry when you were younger, I'm sure. If you took an algebra class and you had a parabola that looked like that, you probably told your algebra teacher that it was symmetric, right? In fact, going through the vertex here, there should be a line of symmetry. Or in algebra, you probably called it an axis of symmetry. And what does that tell me? That's a line of symmetry. It's the same on both sides, okay? So normally we would tell kids, like, if they fold it right down the middle and fold it over on top of each other, which patty paper is really good for this because you can see through it. If this side over here is reflected on this side over here, I can see the same thing on both sides, then it's symmetric, right? That's kind of the idea. Okay, so that's what symmetry is. And I'm sure you've seen that before and done that like in algebra and stuff like that. But what about other things? So for instance, what about these shapes? A, capital A, big old one like that. B, and they've got to be just the way I draw them. They can't be weirdos. If you draw your A differently, then that doesn't mean anything. Well, maybe it means symmetry for yours versus mine. It's different. How about X, Y, and Z? And actually, I've done this with lots of different letters, so you can use H and G and different ones to see what's going on. Okay. And the question is, do these letters have symmetry? And if they do, where would their line of symmetry be? And you can do this with all kinds of stuff. It doesn't have to be letters or whatever. You can do lines of symmetry through a hexagon. If I pulled out the trapezoid out of my pattern blocks, this one's interesting because, let me draw him in. Let me make a copy of him. This one depends. Well, all of them kind of depend. But what about him? If I drew my line of symmetry side to side here, I'm getting a no. That's not going to give me a lot of symmetry. But if I draw it what? Vertical right through the middle here. Okay. Then it looks like this side over here will fold over on top of that side there, and they'll be duplicates of each other, right? So then I have symmetry. Okay. So this would be vertical symmetry. Okay. So what about over here? What about that A? It's the same thing, right? Okay. So if I split it right down the middle vertically, and if I've drawn it correctly, then hopefully it looks like, yeah, it looks like the same thing on both sides. Kind of a small right triangle over here and a small right triangle over here, and they both have legs coming off. Okay. What about the C? Okay, looks like I can do the same thing horizontally, right? As long as I split it right in the middle. Okay. Now, if I had some kind of weird C, I couldn't do it. Or if this was a G, right? If I brought the little thing up and made it a G, then it's no longer got that symmetry. But this C looks pretty good to me. What about that F? Nope. There's nowhere I can split it up and down, side to side. There's also a diagonal sometimes, okay? You can say it's a diagonal line of symmetry, that's okay, but that wouldn't make this guy, right? So this one's a no. What about my X?
Oh, symmetry.
Okay, yeah, it kind of looks like the vertical will work, right? If I do it right. It kind of looks like the horizontal will work as long as they're the same length. And then Summer said, what if I put a diagonal on it? Would this piece here fold down on top of this piece here? Yeah, it kind of would, right? So it has all three symmetries. Yay. Okay, what about this Y? Vertical. Okay, and what about the Z? So if I split it up and down, it's a no, right? We know that for sure. If I split it side to side, we want to say that it would, but the problem is it would have to rotate. Yeah, that's what I'm seeing in here. It would have to rotate in order for it to be up there. Now, there is a symmetry in algebra that goes around the origin, right? And so those guys they would rotate, but this one's not like that. So the only one I could think is, what if I put a diagonal on it? And what would happen if I folded it across this diagonal? What would happen with this piece?
Just extend out.
Yeah, it would kind of make it like this, right? And this piece would probably go a bit more like that. So they don't fold down on top of each other. So they do have this lovely point right here in the middle. If that were the origin, that I could rotate around. And so I'd have that really cool origin symmetry, but that's not one of my normal ones. That happens exclusively whenever I have a coordinate system. Okay. All right, so everybody remember symmetry, right? So y'all can do this homework, I think. All right, good deal. Yay. So that makes us finished with transformations, okay? Plus whatever we get off of presentations and projects and all that good stuff, but we're not going to spend extra time on that. Yay.
Could we use origin symmetry on the homework?
Do you have one in particular?
Maybe number 6.
It's not on a coordinate system, so I would probably say no there.
Okay.
But if you could find some kind of a diagonal that goes through there, you might be able. Interesting. And I will say, like I mentioned a minute ago, if the patty paper will help you, then you might want to trace onto patty paper some of those pictures, and then you could cut them and twist them and that kind of stuff. It might help. Everything good? All right, let's talk proofs. Yes. So we're caught up on our schedule, by the way. We're supposed to be on proofs today. Yes. Not too far off. I like it when we're not too far off. Yay. We go into the syllabus. This is where we're supposed to be. So in the syllabus, we're looking in chapter 13. You don't have to have your book if you don't want to. It's okay. But I'm going to look. So far, we've done the proofs that were like for parallel lines and stuff like that. And we talked about special angles. We haven't done any. We worked through them when we did triangles, if you'll remember proofs. but we didn't do any official proofs with triangles. I said, it's coming, and now it's here. We want to get this in before exam 2 so that I can test you on exam 2 over this stuff. Yes, so that we can say you know how to do proofs and you'll be amazingly smart. It'll be great. I can do it. Okay, so in the book, it's either page 712 or page 688. It's 13.3. Depends on which version of the book you have. And they have a bunch of questions in there, and those are the ones that I'm giving you for the proof project. We're going to pick one and work on it. It'll be great. So I believe that for, I don't want to do number 3 or 4. Those are in your proof project. You want to do number 1? If the point is on the perpendicular bisector of a segment, then it is equally distant from the endpoints of the segment. Let's do that. So this is number 1. Perpendicular bisector of a segment. If a point is on the perpendicular bisector of a segment, then it is equally distant from the endpoints. We're going to have to get a picture with this and see what we think about that. The endpoints of the segment. This is called the perpendicular bisector theorem. Now, this is a little bit different than what we may think about for it, because normally when we think about a line segment, we just think about where is its bisector, okay? So if this is line segment AB, we just say the perpendicular bisector would be perhaps point C. We have a way for constructing those, if you remember, okay? So we made circles at A that had this distance, right? That circle, put it up here, put it down there. We made a circle with B as the center that has this distance for the radius, there and there. And then we found the 2 points of intersection and we drew the segment that went through it. That's how we found the perpendicular bisector, okay? So what they're saying is, we know if this is the perpendicular or if this is the bisector, that this AC is congruent to this CB. We already know that one, right? That's not what they're talking about. They're talking about something on this bisector. Yes, but they're not talking about this. This is given. Because before we would be proving, for instance, that these two are congruent, those two pieces. That's not what they're saying now. They're saying it is a perpendicular bisector. That's the given because it's in the if part of it. Okay. Then it is equally distant from the endpoints. So what they're talking about is point D, for instance. Well, that's sneaky. It's a little bit sneaky. So they're saying the point D is equally distant from A as it is to B. So we know this one because it's in the definition of the bisector. But how in the world do we get here and here congruent?
Could we draw in those lines?
Absolutely.
Triangle congruencies.
And what about those?
We know that AC is congruent to CB, and then CB is congruent because of the identity is the same segment. And so now we have the side equals or side angle side because they're perpendicular with right angles.
Okay. So side angle side. That's not bad, right? It's all right. We can do this. We remember proofs. That's good. All right. So what I'm hearing is, and Maria has sent me side angle side. Perfect. Okay. So use a definition of the bisector. Use the same segment. Use the definition of perpendicular. Right? Side angle side. And now we use CP/CTC. Right? And that'll give me this guy to this guy. So it's not bad. We can do this. You ready? I'm gonna give you a second. How's that? You ready to write it up? You wanna do it together? Let me let you start it. I'll give you a head start. So what would you start with? Start with the giving, Dr. Webster.
Do you want to put the paragraph or the 2 columns?
Okay, I don't care which kind you use, so. I'm gonna do statements and reasons, yes, for the 2 columns. Oh my gosh, we thought we were done with proofs. Stinker. Well, my normal people aren't here today. On the Zoom meeting. Okay. I started it using the picture that we had put together. CD is the perpendicular bisector of AB, and that was given, okay? And you could write that out and make a separate step or whatever, but as long as you have a picture to go with it, I'm okay with you saying that's this first part. Okay, then what? What does that mean that it's the perpendicular bisector? I actually should get 2 things out of that. Okay, I heard AC is congruent to CB. Why do you say that, Ryan? Your reason? Definition of bisector, right? Yep, absolutely. Okay, so that's where we got these 2 pieces congruent. Okay, and then I'm hearing from Mary, angle ACD and angle BCD is equal to, I'm going to do measure of angle ACD is equal to 90 degrees, and measure of angle, she says BCD is equal to 90 degrees. And because of definition of perpendicular, good, she knew I was about to ask. Excellent, Miss Mary. Okay, and CD is congruent to DC, I'm hearing, and that's because why?
Identity property?
Identity. Or same segment, I heard, whichever one you want to say. Okay. I actually need one more little bit from this guy. I'm not quite happy with that guy.
Could we say that those are now equal with the definite, or like right angle congruency or transitive property or something?
Yeah, so I would say, yeah, somewhere along the lines, we need to set them congruent or equal. From the transitive property gives me measure of angle ACD equals measure of angle BCD, right? Okay.
Then we make them congruent because of definition of congruent.
And now we need angle ACD is congruent to angle BCD, I heard, and that's definition of congruence. I like it. So now the reason why I'm getting there is because now I have congruent, two sides are congruent, these sides are congruent, these angles are congruent, right? And whenever I have that, now I have three pieces of my triangles congruent. Now I have side angle side, right? So how am I going to word that one? Oh, there's my triangles. Triangle,
ACD,
okay, ACD is congruent to triangle
BCD.
BCD. Make sure you put them in the right orders. And her reason there is, we already had that one, side angle side, triangle congruency. I like it. Very nice.
Now AD congruent to BD.
And now we have AD is congruent to BD because of BPCTC. Now, we need to be, so first of all, is everybody okay with that proof? Which we went through very quickly and easily saw it, but it still takes a little bit of work to get the steps all out there, right? So just don't stress out, take it one step at a time, you'll get there, okay? But we need to be a little bit careful on our final statement. Remember that what they were saying, that what they said was, if a point, and that's any point, on the perpendicular bisector is on the perpendicular bisector, then that point is equally distant from the two endpoints. Okay, so my question is, did it matter where I put D? Mm-mm. And it doesn't matter if somebody said, well, what about this point down here that's E?
Replace E with D, or D with D.
Point E is the distance to A and it is to B.
Point E is still the same distance here to B as it is to here to A. And Summer said, I could do the exact same proof, just replace it with E, right? Okay. This is where the general comes in, and it's really, really, really nice. So what they're saying is, it doesn't matter where you put this guy, it's going to be equal distance. So I can put one way the heck down here, and it wouldn't be the same distance, of course, as what E is, E to B. This is its own distance. But whatever F to B is, it would be the same distance from A as it is to B. Okay, so that's that general that comes in. And what that tells me is an interesting thing that some of you picked up on and tried to do whenever we were doing some constructions. I normally make my circles go through the endpoints so that when they intersect, they come here and here, right? However, some of you did maybe shorter radii, and it doesn't matter. Do you see what I'm saying? This point that comes up here, that is the intersection point, okay? It doesn't matter if I did it there or if I did it with a different length. So some of you might have said, I'm just going to make my radius be from here to whatever this point is. Okay. boom. And then as long as you use the same radius from the other end, boom. What's going on with my intersection points?
Still on the same line.
They're still on the same line, right? So it doesn't matter if I used smaller radii. They'll still be on the same line. And so that line goes on forever and it's generic. It does not matter where I put the point on there. I'll be okay. Kind of an interesting thought process. So when we finish this up, make sure you know that means this works for any point on the bisector. So any point on a perpendicular bisector to a line segment is equal distance from the endpoints. And I'm going to show you, I don't think I showed you this before, but some of you used it, so I'm going to use it. Okay. There's these three little dots that make a triangle. Some of you use that in your proofs in the last segment. That means therefore. Okay. So if you want to use that, you could say therefore any point, blah, 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 blah. And that's just a cheat. It's a math notation. If you don't want to use it, then don't use it. That's fine. But it means therefore. So if you see that, that's what those people mean. Okay. We good? Question, comment, concerns? So you see where this one was actually, it was about a line segment. The original statement was about a line segment, but it brought in triangles. Of course it did, yes. Okay, so you might not see a triangle originally, but go ahead and draw your picture and then see, okay, how can I work through this? Let's do another one. We have time, we have 12 minutes. We can do it, guys. I know we're all on time change flu right now. Tired. Body hurts. I know, trust me. I don't like it. I just want to stay on summertime all the time, personally. Some people like it the other way. They want to stay on wintertime all the time. You have one? Number 2 is just the converse of that. It says if a point is equally distant from the endpoints, then it is on the bisector. So I think you can work that in reverse. I'm not too stressed about that. Let's do number 3. It's actually in your proof project. Yeah. Like number 3. Number 3 says, if a triangle is isosceles, then the base angles are congruent. Okay. Isosceles triangle means 2 congruent sides. I think we're up to like F, so let's call this guy G, H, I. What do we think?
The vertical symmetry have 5 axes that pop and go P, so the letters are the same. And then we cut it in half, G to J is equal to GJ, therefore 5 and
Okay, and I think that's kind of what I'm hearing over here from Ryan. You said side angle side.
Yes.
So using the bisect the base here. But, okay, so I think that's what, I think y'all are saying the same thing, which is cool. I like that. Okay, so the problem with this one is that if you're just staring at it, trying to start, okay, then you're like, how in the world am I going to do anything with those two congruent sides? And I know that when we do triangle congruencies normally, right, we need two different triangles. I only see one triangle here. So what I'm hearing here in Commerce is, can we make it into two triangles by dropping a perpendicular? Okay. When we drop that perpendicular, a couple of things are going to happen, is what I heard. First of all, we can make sure it's bisecting up here. Okay. It's bisecting down here, the line segment. And the third thing is, perpendicular, so it's what?
180 degrees.
Yeah, 90 degrees. Everybody agree? Okay, so if we drop a perpendicular bisector down into here, then we're going to have these 90-degree angles. So that's my thought that I'm hearing here in Commerce. That'll make these sides congruent because they're bisectors. Okay, this side is congruent to itself, right? So I actually have a couple of different ways to go about this one. Side angle side, 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 just depends on how you see it. Okay. All right. Okay. You probably are either going to do one way or the other. Let me throw this out here. You're probably either going to make this guy perpendicular or you're going to make it a bisector up here. Okay, because I think I heard Ashley saying bisect the angle. Okay. So if you bisect that angle, it's fine. This could be G prime and H prime and I prime. This is my copy guy. Okay, if I bisect that angle up there, it's okay. But whenever I do that, I don't guarantee that it's perpendicular at the bottom. Okay, so I'm either doing a perpendicular bisector to the bottom or I'm bisecting the angle at the top. Doesn't matter, because if I do it that way, then now I have this side, this angle, and this side. Do one way or the other. I don't care. All right. Y'all ready to write it out? Easy peasy. Aren't worried about it at all. Y'all are pros at this now. I like it. You're like, we can do this. If y'all can do it, then we don't have to spend Thursday on proofs. We'll do something else. That'd be great. Okay, I'm gonna start you out. Triangle GHI is isosceles. Because that's what we were given.
We do bisecting. Do we need to create a point the perpendicular bisector?
Yeah, you'll probably want to put in like a K or something there so you can talk about that. So you can talk about the segment from H to K and K to I. Mm-hmm. What we're going to see is whenever we get these things put together that we'll have both things will have happened. We will have that bisected on the bottom and we will have the angles bisected at the top. So it ends up the same. Maria, I'll just give you a special permission. That's no big deal. You let me know about your situation in advance. So, if you'll email me which ones you need, I'll be glad to give you special permission in D2L. Sorry, I'm reading her message. Okay. I'm gonna just do this bottom one. It doesn't matter. There's like 3 or 4 different ways you can go here. I'm going to say GHI, triangle GHI is isosceles because that is what's given. Okay, thank you. That was what was given to me. And I know that that means that GH is congruent to GI. Okay, how do I know that? Definition of an isosceles triangle. Absolutely. Okay, be a little careful because I know that on the test 1, some of you tried to say that the definition of the isosceles triangle was that it has 2 congruent sides and 2 congruent angles, but that is not the definition. The definition is that it has 2 congruent sides. We're actually trying to prove the base angles are congruent, right? That'll give me the 2 congruent angles, but that's not part of the definition. So just be a little bit careful whenever you're talking about definition. I just get those congruent sides. Okay. What did we do next? Ashley said she wanted to bisect angle G, right? And we can construct that. And we know we can construct a perpendicular bisector, and we know we can construct a bisector of an angle. So we know we can do both of those. So we're going to construct, and I'm going to call him GK, which bisects angle G. I think sometimes the ones where you have to add in a side or you have to create a bisector or something like that, those are sometimes some of the harder proofs because you have to put a piece into the picture, so to speak, that wasn't there. You have to create something there. Okay, how can I do that? How do I know I can do that? If you had your word list in front of you, which I did put in week 11's notes, you could see it. But if you don't, then just think about it. What are we doing? We're bisecting an angle, right? So I bet you there's an angle bisector, either conjecture or theorem or something like that. Postulate, she says. There you go. And I don't care which words we're using there, but angle bisector postulate. And we know that what that says, even though we don't have it memorized, is that anytime I have an angle, I can create a one segment or ray that goes through there that bisects it equally, right? Okay, so we know that's what it says. Okay, so I did that. So what does that tell me? Why did we bother doing that? Okay, so I heard angle HGK is congruent to angle IGK because that's what bisector means, right? Bisecting an angle means I get 2 congruent half angles, so to speak. So what's my reason there? Definition of an angle bisector. Absolutely. Got it. And then last but not least, she's using, we've got side angle identity. Good. GK is congruent to KG identity, or we know that same segment, right? And I really don't care which one you call it. The word bank uses identity, right? So now triangle what? HGK is congruent to triangle IGK. I'm going to cheat a little bit because I'm running out of time. We know that those two triangles are congruent because of what? That's side angle side. Triangle congruency. Absolutely. And what was I after? The base angles are congruent. So what was I trying to prove? Good. Angle H is congruent to angle I. And we have a reason for that. It's corresponding parts of congruent triangles are congruent. CPCTC. Yeah, you don't have to remember exactly which C is which one. It doesn't matter. I know it gets a little bit out there. So CPCTC. And then you would just write your therefore statement. The base angles of an isosceles triangle are congruent. Yeah. Very nice. I think that deserves a QED, quite eloquently done. All right, I am 1 minute over time, but I have already called roll. So unless you need something from me, you can have a lovely afternoon. And let me know if you have questions. Thanks. Stop the recording.